and we are already into the penultimate day, that is the day 10th of IVWGST 2022. As this workshop is progressing, it is getting more and more interesting with many renowned speakers across the globe. We are also immensely pleased to see young researchers and dignitaries from various institutions actively participating in all the sessions. Once again, I welcome you all to the first lecture of today's session. And also to put a humble reminder, we have another talk coming up in the afternoon today, which will be presented by Professor Swagarika Mukhopadhyay from IIT Roorkee on the topic 3D seismic velocity structure of the lithosphere and its geodynamic implications for the Western Himalayas syntaxis, and Pamir-Kush Hindu Kush region. So we would like to request one and all present over here to please join us for the afternoon session, which will start at 3 p.m. according to Indian Standard Time. And today we are fortunate to have with us Dr. Wiwit Suryanto from University of Gajah Mada, Indonesia, as a keynote speaker. And the topic of today's keynote lecture is Crustal Anisotropy of Sumatra from Harmonic Decomposition of Receiver Function. Sir, we wholeheartedly welcome you to our session. We are privileged to have with us today Professor J.R. Kyle, ex-Deputy Director General of Geological Survey of India, as the session chairperson, and Dr. Debojit Hazarika from Wadi Institute of Himalayan Geology, Dehradun, as the session course chairperson. Now, I would like to request Honorable Session Chairperson, Professor Kyle sir, to provide his initial remark. Over to Professor Kyle sir.
Thank you very much. It's a great pleasure for all of us to welcome Professor Suryanto from Madagada University. Actually, my association with the university, Madagada University, is long back since 2012 or 11 with Professor Rita. So I really admire that activities of that university in the field of seismology and seismotectonics, landslides, and so many aspects of earthquake hazards. So today we are lucky to listen to Professor Suryanto from Madagada University. We all look forward to listening to your informative lecture. Thank you very much, Professor Suryanto, for accepting our humble invitation. Thank you so much. Over to Anchor, please.
Thank you so much, sir. Now may I request Dr. Debojit Hazarika to say a few words as an initial remark. Over to Dr. Hazarika, sir.
Thank you so much. A very good morning to all of you. On behalf of the third international virtual workshop on the global seismology and tectonics, I would like to welcome Dr. Wiwit Suryanto from UGM, Indonesia. And he will talk on the crustal anisotropy through harmonic analysis. As we all are, many of us are working on seismic anisotropy in the Himalayan region. This lecture will be really interesting for us, and I hope that he will educate us even for the basic steps, how he does it, and the significance of this method. So from my side, I welcome you, and on behalf of everyone, I welcome you, Dr. Suryanto, for this lecture. So it is over to the anchor, please.
Thank you, sir. Before moving ahead, I would like to request Dr. Timanshu Setia from Geoscience and Technology Division, CSIR NIST, to read out an illuminating biodata of Dr. Wiwit Suryanto. Over to Dr. Setia. Dr. Timanshu Setia. Dr. Timanshu Setia, are you there?
Yes, and we regret for the technical glitch we were suffering. Sorry for the delay to everyone. Namaste and a very warm good morning from the land of Assam, a land of grace and a land of plenty. It's my privilege, and I take this opportunity to read out the brief biodata of Dr. Wiwit Suryanto. Dr. Wiwit Suryanto is the Vice Dean for Research and Community Service at Gazamada University, UGM. Dr. Suryanto received his PhD from Ludwig Maximilian University of Munich, Germany. He is a well-known, experienced researcher and a scientist expertise in the field of earth sciences, seismology, and seismic exploration and geophysics. His research interest is wide, which includes earthquake hazard, micro-earthquake, numerical method, signal processing, and seismology. He has published more than 150 papers in international reputed journals, conferences, and seminars. He has been awarded second place for the University Outstanding Lecturer Research category 2021 of UGM. He has also been awarded as the Best Professional Oral Presenter, Indonesian Association of Geophysics 2022. This is just epigrammatic brief of his knowledge, expertise, and research vocation. Thank you, Dr. Suryanto, and moving forward with enthusiasm to hear your lecture. May I kindly hand it over to you, Dr. Suryanto.
Okay, thank you very much for very nice introduction about me. Good morning also everybody. In Indonesia, it's almost noon now. And first of all, I would like to thank to Dr. Santanu to give me opportunity to join not only as a co-chair of this conference, but also to give me time to share our recent study about seismological topic in Indonesia. And today I would like to share the recent studies. This is together with my master students in Gadjah Mada University, Anang Sahroni. And he has a very nice result about the crustal anisotropy along the Great Sumatran fault zone, in the westernmost part of Indonesia. And we try to use not the common method to study anisotropy, which is called the shear wave splitting, but we would like to use the harmonic decomposition of the reservoir function. So today, the outline of my talk, first, I would like to give a short introduction about the tectonics of Sumatra. And then, of course, in this area, there are a lot of studies related to the crustal structure, dynamics, and also the tectonics in the area. I would like to summarize some crustal studies in the region. And then I would like to give also the background why another anisotropy study in Sumatra. And then I would like to show the detailed procedure to do the harmonic decomposition of the reservoir function. And then the result I will show and some take-home message of the talk. I'm sorry. Okay, I'm sorry. So we'll back to the slide. I hope you know where is Sumatra is, the study area. Is it the most, the western part of Indonesia here, the Sumatra Island. It is the second largest island in Indonesia after Borneo, and because the east part, it is belong, half of it belong to New Guinea. And as we know that the Sumatran fault is divided by two segments in the east part and the west part by what's called the Great Sumatran Fault. It is about 1,650 kilometers from the northern part, the Aceh area here, until the southern part, the Lampung area, which is written here, Semangko Fault. And it is very interesting because we can see that the fault is like a sinusoid shape here. It's concave up here in the Sumatra, and then in the middle here we have like the center of the sinus, and then going concave downward here in the south. So it's like a sinusoidal shape, yeah. And the amplitude of the sinus is about 55 kilometers of the fault. And based on the geological study, the Great Sumatran Fault is segmented into for about 23 segments from the north until the south. Yeah. So we can see that it is very interesting location, a very long crustal fault, yeah, the strike slip fault, and it's responsible for damage earthquake in this area of study. Yeah. We remember we have 2009 earthquakes in Padang, thousands of casualties, and also some damage earthquake in Jambi and in Lampong in several years ago. And another interesting thing is we have this volcano. We call it Sinabung volcano here. It is dormant since 1,200 years ago. So it is we said that this inactive volcano, but since 2010 it started to erupt, a very big eruption, and some casualties, some fatalities during eruption until now. So it's like when the volcano is sleeping, but then in 2010 it is wake up. Yeah, until now it's still active and erupt. So we can imagine that it is very interesting to study these areas, especially in the crustal part of the area, because it is responsible to the future hazard in Sumatra. The tectonic reconstruction of this area is also complex. If I can explain here, it's study from Barber, 2005, how the evolution of the tectonic in Sumatra, yeah, from the early Permian, early Triassic, and until the recent tectonics. And we can see that it starts with very complex interaction between the plates, and up here in the right-hand side also a very complex interaction. And until now, the tectonic concept in this area still in study. Yeah, also including this sliver theory about this part of the Sumatran segment in the east, because this is the GPS study in this area, and we can see that in this part, this is the subduction part, and in this part we still have almost the same direction of the subduction. So the concept of sliver plate is still debatable now. So we can see in the east, the west part of the segment is moved to the north, and the east part of the segment moved to the south. And this is also several people try to study the tectonic and also the structure of the crustal in the area, including this is for sea wave splitting for Harmonic. And this is the P and S wave of 2016, yeah, including he interested to map the subsurface of what's so called the Toba volcano, the ancient Toba volcano. It now a very famous lake in Sumatra, the Toba Lake, And from geological study, it is evident that this is the ancient volcano. So the big volcano, which is dome collapse, so the almost half of the body is collapses, and now we have an island in the middle and the lake surrounding the. Can also compare later our result with this tomography study from Kulakov. So what is anisotropic seismic used for? Yeah. As we know that our Earth is not a simple materials. I mean, from geological concept, we always start that the Earth is a layered homogeneous model. But if we look in more detail, especially in the crust, yeah, in the left hand side here, we see that it starts to have a more complex composition. Yeah, for example, in the upper crust, we have especially the brittle materials. And the lower crust, we have a bit plastic materials, and also some interaction, especially in the complex tectonic area, we will have more complex representation of the crust. And this is why the anisotropy study interesting, because we can know in more detail about the crust, and by knowing the crust structure, we will know in more better stand in understanding the tectonic evolution in former time, recent time, and probably for the future tectonic interaction that will be happen in this area of study. And the receiver function is one techniques in seismology which is standard to map the subsurface in understanding the structure of the based on the interaction of the seismic wave, which is trapped in the crust or in the transition of two velocity models. So the tectonic evolution of the Sumatra is, and it is in the mid-Permian. It starts with a very blocky small segment of the Paleothetis Crustal, yeah. And it is here the central part of Indonesia is made by this segment Catasia, and Sumatra is contribution for the Sibumasu and the Gondwana, yeah. And this opening part of the mantle is until now is still interesting area to study in the west part of Sumatra. And until this the recent reconstruction, which is we can see now the Great Sumatran Fault start to grow in this early Triassic. Yeah. The west part of the Sumatra moving to the north, and the east part is moving to the south. And this is in early Cretaceous. This is how the central, the biggest island in Indonesia, the Borneo, is start to created in this area. Yeah. Here it moved again in the north. Yeah. And this is the recent distribution of the with black lines. And concerning the composition of this structure of this block, it's also very heterogeneous, and this is one motivation also to study this isotropic in the Sumatra area. So in the China block, for example, in this area, this part consists of Cetacean flora fossil, and this Bentong Triton. Yeah, it's we found a lot of tin in this area. It's composite by ophiolite. So this is the Sibu Masuk block. It consists of baby mudstone, Fisian flora and fauna fossil, and this tiny medial Sumatra tectonic zone. This composed of high-grade metamorphism and tectonic granite. And the West Sumatra block, the green area consists of tropical Fisian flora and fauna fossil. And the Woila, sorry, it's wrong color, but this is the blue one, is oceanic and volcanic assemblage materials. If we take the west-east profile, yeah, of the Sumatra, for late Cretaceous, we have good composition of this block, yeah, from the Woila Nepal in the west part to the West Sumatra block in the center. Yeah, so we have volcanism in the center of the islands. So this is the moving toward us, so to the south, and this is moving away from us, yeah, to the north. So this is the Bumasu block here in the center of Sumatra and in the China block, yeah, in the most east. And this is the regional setting of the present tectonics. It is studied by Bird 2003 and the Metz 2010. And regionally, it is moving to the northeast, yeah, based on the GPS measurements. It is about 6 to 6.5 centimeter per years. And it is the margin of the Eurasian plate. Yeah, the Sumatra is the margin of the Eurasian plate. And in this area, it has oblique subduction of the Indo-Australia and the Eurasian plate. And this is what I mentioned before, the subduction rate is between 60-70 millimeter per year. Okay, and this is the present tectonic structure and concept in this area. It's based on Bradley, the Metz and IOC and McAfee studies. That the regional structure of the Sumatra consists of the subduction stratigraphic flow. And as I mentioned, that it has about 23 segments, and each segment is moving with some variation from 13.3 and 16 centimeter per CS. Yeah, and the years. So in a very simple structure of the Sumatra is represented in the figure of the upper right image. So the subduction in the east, and here we have a sliver plate, yeah, in between the subduction and the fault, and at the center we have a Sumatran fault, yeah. And in the east part we have Eurasian plate with volcanism, yeah, in this area. Yeah. The sliver plate is one concept of strain partitioning of the subduction direction and the fault. But GPS construction say that it is still parallel to the subducting plate. So it's still need more detailed information in this area. So if we again make a profile from the southwest to the northeast part of the Sumatra Islands, crossing the Toba Lake here. So we see that the present tectonic is very
Is there some problem?
Yes, sir, there's some sudden problem from Suryanto's end.
yeah.
Dr. Suryanto, if you can close
Back.
your camera, then it will be good, I think.
Okay.
Yeah.
I hope you can.
Please close your camera so save your bandwidth.
Yes, I have a problem with the bandwidth of my.
Yes.
I'm sorry.
Yeah.
Can you
please
see?
close your camera. Yeah.
Okay. Yes, you can see it. Okay. I'm sorry. I'm continue with the tectonic stress study from Heidbach. Yeah. He used the single focal mechanism to plot the orientation of the structure in the west part of the fault, and some of the west part of the Sumatran. They use the borehole data because we have a lot of oil well in this area, and they made structural studies based on the well in this area and providing this kind of result. And it suggests it's a complex stress direction. Yeah. But if we can look in more general, that stress direction in the forearc and back arc is normal to the trends, so it is in the northeast and southwest directions. And along the Sumatran fault, we can see that it is still consistent along the Sumatran fault, which is in the direction of north to the northeast. And the earthquake mechanism along the subduction is normal to reverse. It is actually it's normal in this area. And along the Sumatran fault, it is mostly dextral strike slip, and it is consistent with the tectonic of the Sumatran fault. So again, it is very interesting to study the crustal anisotropy in this area to understand in more detail about the Sumatran fault. So concerning the method, it is actually also a lot of studies in Sumatra, yeah, and also using reserve function, but for anisotropy study with reserve function is still rare, yeah, in Sumatra. It's starting by Bianchi et al. To introduce this method. Usually, reserve function is used to study the Moho discontinuity and then the upper and lower crust structure, yeah, using the inversion of the reserve function. But Bianchi introduced that this method can also try to looking for the anisotropy body. So he made this study in 2010 to understand the overlapping Moho depth, yeah, here in the yellow, the depth of 25 kilometers, and this the incline Moho depth. Mediterranean areas, and you can find then we can see the anisotropy part in this area, yeah, in between yellow and the red color here, and he introduced this. This is because of this the anisotropy, and we can see the pattern from the reserve function. And this is a very nice validation of the method, which is comparing the anisotropy from the reserve function to the deep crustal borehole in Germany, in the KTB borehole. It is very interesting because the result is very convincing that the direction of the anisotropy, yeah, this is the low velocity axis of the anisotropy is related to the direction of the structure along the area of studies. It is based on the borehole data. Convincing because the evidence of the anisotropy from the reserve function is revealed by this study. And this is very positive correlation between the foliation and fault with the anisotropy from the reserve function. And then this become popular, this method, after these comparisons. For example, there are another study in US, in the Southern California. Although at the beginning, these studies suggest that the anisotropy is quite random here, quite complex. But if it reconstructed to the ancient structure, it is very consistent with the direction of the structure at that time. It is in 36 million ago. So lower crustal anisotropy in Southern California is very consistent with the subduction of the Farallon plate to the North America plate in 36 million years ago. So it's also very convincing. And this is also the anisotropy using reserve function studied in the US in the Wine River Range in Wyoming. and the fault strike and the depth mapping can be obtained by the reserve function. So it is different with the standard shear wave splitting study for anisotropy, which is the anisotropy is the superposition of all the ray path of the seismic wave. But with this reserve function, we can try to find the anisotropy for its depth. So instead of only have the direction of anisotropy, in reserve function, we can also get the depth of the anisotropy media. So this is one advantage of using this method. So maybe for the student, it is very on what is the reserve function. As we know that the seismogram, which is our recording of the ground motion, is the interaction between source, medium, and the instrument or seismometer. So this is the convolution operation. So in the time domain, we have the seismogram, the U as a function of T is equal to the source, the earthquake source, convolved by the medium. This is the Earth model, and convolved with the instrument response. In time domain, convolution is equal the seismogram. In the frequency domain is the multiplication of the source in the frequency domain, and the medium in the frequency domain, and the instrument in the frequency domain. So if we remove the instrument response from the equation, so it means that we have only have the structure and the source. So if we want to have the structure, so we should deconvolve, so the inverse of the convolution. So we deconvolve the source and the reserve function. So the source here, we use the vertical component of the seismogram. So we use the three component of seismogram: the vertical component and the horizontal component, which is consists of the east-west and the north-south part. So the vertical component, we can see that this is the source, and assuming this is the source, we deconvolve this with the horizontal component to find the velocity model, but still in time domain. So this is the result. So if we have this wavefront, from this is assuming that we have teleseismic signals. So we have plane wave here going to the seismometers, and we have several phases here. This is the black is the P wave converted to still the P wave, and we have this event in from below it is P wave, but in this transition in the MOHO, the interface it changed to the S wave. So the green is the S, and we have this PS wave, and it will be represented here in the reserve function. And we have another combination, the PPPS and the PPSS and PSPS, coming later here. So this is the typical anatomy of the reserve function, and it is show that it related to the structure. It means the between PP and PS, it's related to the depth of the MOHO, and also between PPPS and PPSS, PSPS, it is also related to the depth of the MOHO. Usually we then import this reserve function to find the velocity model at the subsurface. But in this case, we decompose this reserve function into the anisotropy properties of the subsurface. What is the seismic anisotropy? So seismic anisotropy is the characteristic of the medium that it is not all the velocity of seismic velocity in the medium is not the same in all direction, but it is different in every direction. So usually for modeling the signals of if we make a simulation, we assume that the system is isotropic, yeah. But isotropic, and we have this strain. The elastic tensor here is more complex than isotropic, yeah. But if we assume that it is isotropic, almost all of the component of the elastic tensor is 0 except in the diagonal of the
He is disconnected.
Layer, which is horizontally in between the upper and the lower part, and assuming this is we have the inclined anisotropy body, anisotropy layer, yeah. What will the residual function at the surface? So we make this consists of upper part of the crustal, 15 kilo, and the lower part of the crustal, and this is the mantle, which is all isotropic. Then the radial component of the residual function is almost equal like this, yeah. And this is the transverse is almost flat, yeah. So no amplitude variation in the function of back azimuth. So this is the back azimuth of the event to the station, and we can see that for isotropic model there are no amplitude variation, yeah. And also there is no energy in transverse component for isotropic. So this is the second case, which is still isotropic, but it's inclined, yeah. We can see that with the dipping layer here, which is still isotropic, the maximum between the up dip and down dip, this one, and the amplitude periodicity in the function of the back azimuth is 360 degrees, yeah. So we can see here when the inclined isotropic model coming, then the residual function will also change. And now if we have the anisotropic layer, horizontal layer, yeah, here, this residual function, yeah. The radial component of residual function so that the maximum amplitude in the direction of the anisotropic axis, and in the transverse residual function, the minimum amplitude is in the anisotropic axis direction. And the amplitude periodicity in the residual function is a function of back azimuth, is about 180 degrees. Yeah. So this is if we have the anisotropic dipping layer, yeah. We have also this feature, yeah, the radial component, so that the maximum amplitude is in the anisotropic axis direction, and the transverse reserve function, the minimum amplitude is in the anisotropic oxidation, and the amplitude periodicity in the function of back azimuth, is 360 degree. So now we go to decompose the reserve function into their harmonic properties of the radial and transverse. For anisotropic, which is dipping symmetry axis, we have the periodicity of P power 2. Periodicity of pi, and the phase shift is P over 4. And then we, these are from BNC, so how we decompose the harmonic component of the reserve function into these 5 harmonic components. So what we call the A as a function of depth, B1 as a function of depth, B2, C1, and C2, both of the function.
Dr. Timangsu?
The trend of the direction, it is like particle motion in normal seismogram analysis. For each component, for example, the B1 and B2, which is the dipping axis anisotropic contribution, both in the north-south and the east part, we can calculate the orientation, the trend of orientation of the anisotropic. For example, if we want to know the overall anisotropic structure, we can simulate the particle motion between the B1 and the B2, and we can see in which direction the trend of the anisotropic is toward. But if we want to have in some depth, we only choose at up to the depth of the target, and we also then calculate the particle motion to find the linear trend direction. To do this, we should make the velocity model, but it's still in time domain, so we need to change from the time domain into the depth, the distance, and we make the time to the depth conversion. So we make time shift between this in second, the time into the depth. And we do the procedure based on Barros and Asup Kau in 2011. Okay, then we go to the study area. And this is several applications that we use. We, of course, using standard OpSpy software to pre-processing the data. And we use this RF Pi, yeah, from several outlets. And for plotting, we use Matplotlib, and to map the result, we use QGIS, the open software for mapping, and Inkscape for making the graph. I will fast going to the flowchart of the processing. For each station, we do conversion and then doing the harmonic decomposition, and we end up to come to map the result to interpret the result. So this is how we do from step by step from the raw data. For example, this is at the center of the study area, the PKNI station. The raw data is something like this, and then if we rotate it toward the event, we have the right-hand side.
Pardon, sir.
Yeah.
So sorry for the interruption.
Yeah, sure.
So very sorry for the interruption. So we just require a help from your side. So can you just switch off your video so that we get the network very clearly? Actually, we are facing some problem and the video is stuck in middle. So if you just means off the video, so then we can play the slides over here and your voice will be very audible.
Okay, good.
Okay. So once again, very sorry for bothering you.
No problem. I'm sorry.
An interruption for the interruption.
No.
Thank you so much, sir.
Yeah. I have a very bad connection here. I'm sorry. I forgot to switch off the video because it's really disturbed the presentation. Okay, I back here, and this is the process. Okay. And yeah, we end up with the calculation of the weight of the quality of the data using the signal to noise ratio. And yeah, we end up with this radial component of pressure function as a function of back azimuth, and the transverse component of the pressure function as a function of back azimuth. So this is I again show the example of the result. So the right side here is the deconvolved reserve function in the BKN station. Sorry. To make sure that you have the same. Okay, and the next is the time to depth conversion. What we do is from the reserve function, we try to calculate the right parameters, and then we do the depth, time depth pair calculation, and we doing the time shifting in the frequency domain, and then determine the amplitude, and then finally we get the reserve function as a function of depth. And this is what we have from the time domain reserve function, which is relating the amplitude of the reserve function. So the impulse response with the time, and with in the right hand side we have the reserve function as a time of depth. Yeah, it is a bit like stretching, yeah, but it is all related to the structure. And then from the depth converted reserve function, we decompose, as I mentioned before, into the 5 components. So this is the dipping component, and this is the horizontal harmonic components of the anisotropy. And then we do the direction analysis using the particle motion. And what we do is we make the multiple reserve function, and it's grouped into 10-degree back azimuth beam, and we have this kind of data. And then we have the multiple reserve function, and we finally do the harmonic decomposition. So this is the example of the harmonic decomposition at the BKNI station. Yeah. And then finally we decompose. I think this is I already mentioned before. And then finally, for example, if we want to know the anisotropy up to the depth of 15 kilometers, we put this part and we do the analysis. And using the linear regression, we find the direction of the anisotropy of the depth of 0 to 15 kilometers. This is another example. For example, the C2
We once again apologize that we are facing some connection issues. We are not unable to receive the video. So most probably the session will start as soon as we receive the video. Dr. Suryanto.
Yeah, I'm sorry. So I'm sorry, it's disturbing.
Yeah, yes, you're audible now.
Yeah. We have very bad connection today. I don't know. Usually it's fine, but today we. You see it? Okay. Okay. So.
Yes.
Yeah. Okay. So I'm sorry. I will move faster now. And comparing to other study, for example, from GPS measurement in the yellow and the surface motion from GPS green, and the focal mechanism in the purple, we see that our anisotropy study quite consistent with the previous result and showing the similar pattern to the tectonic structure. And as mentioned before, that we have also a quite good tomographic study in the center part of the study area, which is in Toba Lake, yeah, in central Sumatera. And if we plot the anisotropy, it is very consistent with the tomogram image in the depth of 10 kilometers. In this part, you see that the purple anomalies, the high velocity is very good reconstruct with the anisotropy from the reserve function. And at the depth of 30 kilometers, we use the decomposition at the 30 kilometer also, and it is still showing a very nice result comparing to the tomogram image. And if we also compare the cross-section of the tomogram image with our converted to depth reserve function, we see that the mafic crustal, the upper part and the lower part of the crustal can be better imaged by this reserve function study. Yeah, even better than this tomogram in terms of the interface. And this is the depth conversion. The line is created by Kulakov, yeah, from the tomographic image, and it's related to the phase, which is consistent with. Again, the comparison between the reserve function anisotropy with the shear wave studies. from Chandra, yeah, and both in the upper layer and the overall crustal, yeah. This is also using local COA splitting from Collins 2013. And if we look in more detail of each segment, it is also interesting that the anisotropy is also consistent with the structure in each segment. This is the ranum B segment in this area. This is Toru segment. It is also a very good relation with the structure. This is Ancola Barumun segment. It is very nice, even if the structures is here like this. It is the same trend with the anisotropy from the function. So this is the Sumani segment. It's also still very consistent. You see here, it's very nice. And this is the Sutili Siula segment. In the soft part is also consistent, and looking for the trend and the confidence level, as I mentioned, that the confidence level is calculated by measuring the thickness of the particle motion. So we see that in the place where the confidence level is high, it is very consistent with the structure, and still, although if it's a bit higher, then it still have a good deep structure. The depth of it from 15 to 30 kilometers still have the same trend. So it is suggests the same previous result that the structure in the Sumatra is continuous from the surface until the mantle. So from our study, it is also suggested that we have showing the same result, that the trend is still the same from the upper crust to the lower crust in Sumatera region. This is also showing the same result, and it's comparable also to surface wave anisotropy topography from Wang in 2022, the same studies. So, and also comparing to the tectonic morphology in the area of study is also still consistent with the regional tectonic model of the Sumatra. So this is in the ranum segment, we have a lot of station. Also, it is very good comparison with the structure. This is Toru. This is the depth structure. It still have the same pattern with the near surface. Okay, for take-home message, I would like continue for the next study for inverting the inverse pressure function. Okay, I think it's all. Thank you very much. I'm sorry for the technical problem. Yeah.
Thank you so much, sir, for such a significant and elaborate talk. However, we faced some technical glitches in receiving the audio-visual, perhaps due to internet connectivity in middle of the lecture. We regret for the same and sorry for inconveniences caused which was beyond our control. Before moving ahead, I would like to announce that we will take 3 queries from the attendees. I request all the participants with a query to kindly raise your hands, and accordingly we may ask you to unmute yourself to clean your query from the speaker. Also, the participants may please send the rest of their unattended questions to the email ID of the convener of this workshop. Thank you. Now, may I request Honorable Session Chairperson, Professor J.R. Kaisa, to provide his final remarks. Over to Professor Kaisa.
Thank you so much. Congratulations, Professor Suryanto. It was really very detailed study, detailed crustal studies below Sumatra island, and the result slides at the end were very fascinating, and I was really delighted to observe your result, how they are different from different tectonic domain. That's what I was wondering. But still I have a query, Professor Suryanto, that whether broadly you have correlated that the anisotropy is along the Sumatra fault, but whether meticulously if you observe whether it is there is some difference between the Sumatra fault zone and the volcanic zone, whether there is some difference in anisotropy trend, and also in the silver part of the plate, whether there is a change of anisotropic trend change between these three. In general, they are along the Sumatra fault, but I am just asking whether meticulously, if you observe, whether there is some difference between the silver plate, Sumatra fault, and the volcanic zone, the crustal anisotropy.
Thank you very much, Prof. Khayal, for the question. Yes, I showed because the prominent evidence for comparing our result is also mentioned about the volcanism in the Sumatra, but you write that in the east part of the fault, which is very dense volcanism in this area, and of course it will very interesting to study in more detail about the effects of the volcanism to the anisotropic structure. So volcanism subsurface model in the volcano, except for Toba volcanism. Yeah, from Toba volcanism, we can see that even the horizontal map of the tomogram image is very related to the anisotropy, but also from the depth we have the good correlation between the partial melting of the magma. It is very good imaging by the anisotropy. But other volcanism properties we need for the next project. Yeah, for Sky. So thank you very much.
Thank you so much, Professor Suryanto. Thank you so much.
Thank you very much.
Over to Anchor, please.
Yeah.
Thank you so much, sir. Now I would like to request Dr. Debojit Hazarika, sir, to provide his final remark. Over to Dr. Hazarika, sir. I think he's not there at this moment. So now may I request the participants, if they have any query, to kindly raise their hands and ask questions. Yes.
There are participants
Question
who
from Adenika. From Adenika. One question from Adenika. Please unmute yourself.
Yeah.
Adenika Charles.
Adenika, please unmute yourself.
Adenika, please.
Adenika Charles, please unmute yourself and ask your query.
In the meantime, Dr. Hazarika sir also available.
Okay.
Yeah, actually, I was disconnected for some time. I was disconnected because of some issue. May I interact?
Yes, please. Yes, please.
Okay. Congratulations, Dr.
Thank you very much,
Professor Suryanto.
Yeah.
It was a really very interesting talk for all of us, and particularly I was very much interested to understand the method that you are using. In fact, we are also working in the Himalayan region, the seismic anisotropy of mantle, and also the upper crust based on the shear wave splitting.
Yeah.
So in recent times, we are trying to implement this harmonic analysis for our data. So there will be many interactions, I think, possible with you. But the thing is that unfortunately today I got a little disturbance in between. I couldn't hear you while you were explaining. You might have explained very nicely the methodology and other things. So I think if you permit in some other time, we will invite you to RDI Institute for a lecture so that our students and we all, we are interested to understand this harmonic analysis and its tidbits little bit from you.
Sure.
So rather than asking here, because here we have already taken a lot of time from you, and many questions will be from our student side. So I want to interact with you a lot regarding these methods, and I got a lot of interest from the results that you are getting from the Sumatra region also. So thank you so much for giving such a wonderful talk, and I think I will communicate to you, and we will fix some. We will take some time from you. Then we will interact a lot with you.
Okay, thank you very much.
I think you will give that opportunity. I will communicate to you through email, and then we'll fix some time, and we will discuss. Yeah, we'll invite to our institute.
Okay, thank you very much. And also, I'm waiting invitation from Dr. Santano to visit India. Actually,
yes, most welcome. Most welcome. By the way, I have a question. How many stations do you have? How many seismic stations do you have for Indonesia?
From Indonesia, we now have around 500 stations from the Sumatera till the east part of Indonesia. So almost 500 stations.
It is operated by your university or different institute?
Yeah, we because the people from BMKG, some of them are doing a master or PhD student in our university, so we can access the data, especially for collaboration and for research. So yeah, we have access.
Yes. So about to Adenika for his question.
Adenika sirs, if you are present, please kindly unmute yourself and ask your query.
Maybe he's having some technical glitch, so please proceed.
So, due to time constraint, we would like to end our question and answer session here. So I would like to request all of the attendees who have their queries to kindly email it to us, and we will forward it to our concerned speaker and send their replies to your respective email IDs. Now, may I request Mr. Pasuja Borthaku, Junior Research Fellow of CSI Northeast Institute of Science and Technology, to kindly deliver the vote of thanks. Over to Mr. Pasuja Borthaku.
Thank you, Mr. Navajyoti. Namaskar and good morning to all. As today's event has come to an end, it is my immense pleasure to convey heartfelt thanks to each and everyone on behalf of entire CSI NIST family and the organizing member of IVWGST 2022. I would like to take this opportunity to thank Dr. Wiwit Suryanto sir for accepting our invitation and delivering such an educative talk. Thank you so much, sir, for such a wonderful and edifying lecture. It was a great pleasure to have you as a keynote speaker for this event. Our deep sense of gratitude goes to our director, sir, Dr. G. Narahari Shastriji, for his tremendous support and guidance in each and every step of the workshop. Our heartfelt appreciation to the international advisor, Professor Andrew J. Michael, USGS, Professor Dapeng Zhao from Tohoku University, Japan, and sessions chairperson, Professor J.R. Kayal, sir, the former Deputy Director General, GSI, Government of India, for their thoughtful insight for these live sessions. I find this opportunity to express our profound gratitude to the session's co-chairperson, Dr. Debojit Hazarika, Wadia Institute of Himalayan Geology, and Dr. Santanu Burwa, sir, the convener of IVWGST 2022, for his devotion towards this international workshop. A special thanks goes to all the members of technical and organizing committee for their hard work and dedication. Last but not the least, I express my deep sense of appreciation to all the attendees for their active participation. We, the IVWGST team, wish for your continued support throughout this event. We have another lecture today at 3 p.m. Indian Standard Time. Our keynote speaker for the second session is Professor Sagarika Mukhopadhyay ma'am from IIT Roorkee. I repeat, we have another session today at 3 p.m. Indian Standard Time. Our keynote speaker for the second session is Professor Sagarika Mukhopadhyay ma'am from IIT Roorkee. On this note, we are signing off from today's event. Namaskar. Dhanwad.
Thank you very much for kindly invite me and join this. Very nice to meet you all.
Thank you. Thank you, Dr. Wiwit. Thank you so much for your.
See you later. Bye bye.
Thank you. Thank you.
Yeah,
Thank you.
always.